Okay, topic 7 is the last topic in our systems of equations unit. And really, this topic is actually about systems of inequalities. So we're not going to talk about equations today, but we are going to talk about systems where you still have two inequalities working together to come up with some solutions. So the first question here says, consider the point 1, 2. Is it a solution to the system of inequalities found below? Well, before I answer, I'm going to jump down to this box. It says, how can we prove this? In other words, how can we answer it? Well, we've got many methods that we've learned so far, 3 specifically, but it says systems of inequalities cannot be solved using substitution and elimination. We have to use graphing and by plugging in points. So the only 2 ways you can solve an inequality. The reason why is substitution relies on knowing what something is equal to, and we don't have that with an inequality. And elimination relies on making sure that the equations have an equal component. So because we don't have any equal signs, we can't use substitution elimination. We can only graph and then plug in points. So let's start by plugging in points up here. In other words, a point. They've given us 1, 2, which means my x is 1 and my y is 2. So let's start just by plugging in to see if this works for the inequalities. In other words, if it makes the inequalities true. So 3x, which would really be 3 times 1, plus 2y, so 2 times 2, is supposed to be greater than or equal to negative 2. So we'll see if this works. So that'd be 3 plus 4. So 7 is greater than or equal to negative 2. Well, yes, that is true. 7 is greater than or equal to negative 2. So far the point does work. It's a solution to the first inequality. But let's try the next one. X plus 2y. So 1 plus 2y, which is just 2, is supposed to be less than 2. So I've got 1 plus 4, so 5 is less than 2. Well, no, that does not work. 5 is not less than 2. So my final answer here, is it a solution? No, not a solution. But I want to prove that again with graphing, okay? So let me switch colors here to switch methods. So let's talk about graphing. If I were to take these exact same 2 equations and put them on a graph, first I would need to solve them for y equals mx plus b, right? Let me write them over here so I can zoom in on my screen and not lose them. So, let's take the first equation. I need to, actually let me move this down a little bit. So I need to subtract the 3x over, divide everything by 2, so y is greater than or equal to negative 3 halves x minus 1. Okay, there's my first equation that I'm going to put on my graph. Second equation, again, I need to move my x over, divide everything by 2, so y is less than or equal to negative 1 half x plus 1. Okay, so those are the 2 equations I'm going to put on my graph over here. Now, I say equation, sorry, inequality. So the first one, I've got a y-intercept of negative 1, slope of negative 3 halves. So I'm putting these points in here. Now think back to unit 4, I guess that was, where we first learned how to graph inequalities. Greater than or equal to means that I've got a solid line, not a dashed line. And when I read this as y is greater than or equal to, that means I need to be shading up the y-axis. I want to shade all the y's that are greater than that line. Okay? Second line, y is less than or equal to negative 1 half x plus 1. Let me switch colors here. I'll use blue. So plus 1, here's my y-intercept. Negative 1 half means down 1 over 2, down 1 over 2. Okay, I'm going to connect. Again, it is equal to, so I'm allowed to use a solid line here. It's not always the case. And I see that y is less than or equal to, so I need to be shading down the y-axis. So I'm going to shade all of this. Now, well, that's all great and dandy. If these systems are supposed to be these inequalities are supposed to be working together, what I really care about is this double shaded region in here. Okay, it was shaded both green and blue. So this little section is where all of the systems lie. Okay, and obviously it expands and goes on like this forever. But any point that is in this gray region is a solution to the system. Anything that's not in that area is not a solution. So going back to this problem, the question asked about the point 1, 2. So let's go graph 1, 2. That'd be right here. Well, that's in the green area, but it's not in the desired gray area, right? So that makes it not a solution. That's why it worked for the first equation, but not the second one, okay? Now, this point, is it a solution? Well, yes, but it's one of many. That's a solution, that's a solution, that's a solution, that's a solution, that's a solution. These are all solutions all along this area, okay? So there's an infinite number of them because it's an inequality, okay? So unlike with normal equations, the intersection point is not the end-all be-all. That's one of many, many solutions, okay? So let's keep going. Because graphing and plugging in points are our only options, you're going to find yourself graphing a lot here. So if you feel like you're good at graphing, feel free to pause the video, fast forward a little bit, speed up the speed, so you're not bored with me graphing. Okay, so first I need to change these into y equals mx plus b. Okay, I'm going to subtract my x, divide by 2. I'm just going to rewrite this first one for neatness sake. Okay, I need to graph these. So I'm starting at 4. My slope is -2. I connect. I do get to use a solid line because it is greater than or less than or equal to. And again, because it is less than or equal to, I'm going to shade down the y-axis. So all of this gets shaded. Okay. So then switch colors here. Actually, let's use blue. Y is greater than or equal to -1/2 x plus 4. So same y-intercept, but again, that doesn't necessarily mean anything great. -1/2 x. Solid line again. And y is greater than. So this means I'm going to shade above the y-axis. Oh, I don't want to use pink. I'll use blue. Above the y-axis. Or up the y-axis, I should say. Okay, so the only area that's going to be double shaded, make it purple, is this little area right here. So this is where all of the solutions to this graph will be. Okay, let's see. Make sure I follow the instructions. Yep, I'm just graphing. All right, so next set of problems. They already have this one solved for y, so that's good. Y is less than 3. Got to solve the next one for y, so I'm going to subtract 8x from both sides. I'm going to divide by -4. Now remember, when you divide by a negative, that's going to flip the symbol around. It's very important you remember that part. Okay, so y is greater than 2x minus 3. So the first equation, y is less than 3. Well, that's ahoy, right? There's no x, so that means it's just a horizontal line at 3, okay? But remember, there's no equal to sign here, so it has to be a dotted line. It does say y is less than, so I need to shade down. Okay, now let's go to the second one. Y is greater than 2x minus 3, so here's my -3 for my y-intercept. Slope of 2. Again, a dotted line because it's not equal to. And y is greater, so I need to shade above or up the y-axis. Okay, so I'm looking for the double shaded region. That's where it's both pink and blue. In other words, it's purple. So that's this whole area over here. Okay. Again, solve these for y equals mx plus b. I'm going to subtract x. I'm going to subtract x. Now you may notice these have the exact same slope and the exact same y-intercept. Typically that would mean that it's the same line. It's coinciding, right? But let's just see how this one plays out. So I'm going to graph the first one. Y-intercept of -2. Negative x is my slope. Okay. It is going to be equal to, so I can make it a solid line. Okay, y is supposed to be less than, so when I shade, I want to go below the line. Okay, so now let's go to the other one. Well, obviously it's going to be in the same exact location. -2 is my y-intercept. My points are all going to be the same, but this one is a dotted line, right? Dotted line. So it's not exactly the same. And then y is supposed to be greater this time. So I'm shading above. Well, if I'm looking for the double shaded region where it's been shaded twice, is there any region that's been shaded twice? There's not, right? So this is actually an example of no solutions. Okay? But we didn't know that until we graphed it and saw that it wasn't going to be shaded twice. So don't just assume if it's the same y-intercept and the same slope that it's going to be infinite solutions, because that's only when they're equations. This is something totally different. Okay? So you have to graph an inequality to be sure. Let's see. Let's keep going. So number 4. First one is good to go. Second one's good to go. The last one, I just need to move my x over. So we graph the first one. X is greater than 0. Well, that's a vux, right? And it's 0. So that means it's just the y-axis. It's not equal to, so I have to draw a dotted line. And x is greater. So that means I'm going to shade to the right because I'm talking about x is greater. Okay, second line. Y is greater than 0. So that's a hoy. Since it's 0, it's just the x-axis. Dotted line. Y is greater. Okay, now there just so happens to be a third line here. Let's do green. So my y-intercept here is 6, and the slope is -1. Again, a dotted line. Okay, and this time, y is less than, so I'm going to go down on this one. Now, for this problem, there just is a tiny little triangular area that has been shaded all the colors. Pink, blue, green, everything in this little triangle, okay? So that means all my solutions to this graph have to be in this region, okay? Now, there are still going to be an infinite number of solutions because you could zoom in forever. Picture your iPad. You could zoom in forever like this and forever get tinier and tinier and have more and more decimals. So just because it's kind of outlined by these different boundaries doesn't mean that it's not infinite anymore. There's still an infinite number of solutions. Okay, and I'm actually going to pause now just to go back and just kind of give you yay or nay about solutions. Again, point over here, is that a solution? No. Point over here? Absolutely not, because it's not in any shaded. Over here? No. Purple? Yes. Okay, and I do want to point out, is this a solution, the intersection? Yes. Is this a solution, a point on the blue line? Well, we're allowed to use the blue line, and it's in the red shaded area, so yes. Okay, over here. This point would be a no. This would be a no. This would be a no. This would be a yes. Okay, but here's something different. The intersection, that's a no here. Okay, because those are dotted lines. You can't use anything on the line at all if it's dotted, right? So these would also be no's. If it's on a dotted line, you can't use it. Okay? So this last one, again, that's further proof why this is a no, because we're not allowed to use the line at all, and then there's no other region that's been double shaded. Okay? So then over here again, no, 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 yes, and here, but then again, the lines are all no's because they're all dotted lines. Okay? All right, so now write the system of inequalities for the graph below. This time they're wanting us to write the inequalities. They're not wanting us to actually graph anything or list any solutions. They're wanting us to write the equations, or in other words, the inequalities. So let's start with the solid line. If it's solid, that means it's going to be greater than or equal to, okay? So the solid line has been shaded up. All of the shading is above that line, so its y is greater than or equal to. My y-intercept here I can tell is a 3. And the slope looks like it's just a perfect -1. Up 1 over 1, up 1 over 1. So negative x plus 3. Okay, the dotted line. This one, again, has also been shaded up. Everything is above that graph. So y is greater, but not equal to. Y-intercept here is -3. And the slope looks like it is up 2 over 1. So 2x minus 3. Okay? It's kind of hard to read. It's a negative x plus 3.